Hello, I'm Dr. Matt Helmers with Iowa State University and the director of the Iowa Nutrient Research Center. We're fortunate to be out at one of the Iowa Conservation Reserve Enhancement Program wetlands today with Dr. Bill Crumpton that's been working on this technology for a number of years. And these practices are being put in place to help us reduce downstream nitrate delivery, intercepting that tile drainage and water and reducing nitrate delivery. Thanks for joining us today, Bill.
Glad to be here.
So one of the questions I would have is, these are being put in to help us reduce downstream nitrate delivery. How do they go about removing nitrate?
So the primary process involved in nitrate reduction in these types of wetlands, ones with really heavy non-point source loads, is denitrification. So denitrification is carried out by anaerobic bacteria. The heterotrophic bacteria, they use organic carbon as an energy source. They use nitrate as an electron acceptor rather than oxygen. And they denitrify nitrate to dinitrogen gas, N2 gas. That's 80% of the atmosphere.
So what impacts their overall nitrate removal or the performance of the wetlands? What are some of the factors that influence their performance?
Okay, so the factors the primary factors that affect their average long-term performance is the amount of water that goes into them, so the hydraulic loading rate. That's the volume of water divided by the pool area. The temperature affects their performance. Nitrate concentrations, the higher the concentration, the more mass they remove. Those are the primary factors that we have some control over: hydraulic loading rate, concentration, and temperature. We don't have a lot of control over concentration or temperature, but we do have control over hydraulic loading rate. If we make the wetland larger, hydraulic loading rate will be lower. The wetland will remove a larger percentage of the nitrate that it sees.
So what might we expect as we think about different hydraulic loading rates and the size of the wetland in relation to the watershed? What might we expect for nitrate removal?
So hydraulic loading rate will be related to the pool area and the contributing area to that wetland. And people can relate to that a little better than just hydraulic loading rates, right? So a wetland that was 1% of its contributing area, right? So a catchment was 500 acres, a 5-acre wetland sitting at the bottom of it. That wetland would remove close to 50% on average of the nitrate that it sees.
So these wetlands, at times we'll see some of these wetlands with a lot of emergent or submergent vegetation. Does that vegetation matter as we think about the performance from a nitrate removal standpoint?
For habitat it matters a lot, but for nitrate removal, the wetlands will function with or without extensive emergent vegetation or submergent vegetation. The vegetation, especially emergent vegetation, greatest influence is it can affect the way water moves through the wetland, right? So if you had really dense stands of emergent vegetation and a channel down the middle that was open, then you'd get a lot of short-circuiting of flows. The vegetation would resist flow. The flow would tend to short-circuit down the middle of the wetland, down the channel. That would reduce performance. On the other hand, if you had uniform emergent vegetation across the wetland and the water was forced to move through it, you could improve performance because bacteria associated with the submerged portions of that vegetation, especially standing dead vegetation, could support denitrification, right?
So does it matter how deep these wetland areas are for nitrate removal?
It matters how deep, but they're designed within a fairly narrow bound, right? So the wetlands have to have at least 75% of the total pool area has to be shallower than 3 feet. You can have deep areas, but they can be no more than 25% of the total pool area, right? So the wetlands are, on average, very shallow. On average, they're about 2 foot deep. The average depth for CREP wetlands is about 2 feet. They may have areas that are 8 feet deep, but their average depth is 2 feet. So they're predominantly shallow margins with a little bit of deep water toward the middle, right? So there's not a lot of difference in the average depth among the CREP wetlands because of those constraints, right?
So you've been working on the design, monitoring of these types of wetlands for the better part of a couple decades. During that time, has the design of them changed to try to improve their performance from a nitrate reduction standpoint?
Yes, it has, right? So the primary changes have been the use of submerged berms to make sure water didn't short circuit through the wetland. So we make sure all the prior channels in the wetland, those are plugged at intervals, and we have shallow submerged berms to make sure water moves in a fairly efficient manner and it makes good contact with most of the wetland pool. The other change that we've made is in areas where there are more erosive environments, higher energy landscapes, they'll build sediment detention basins upstream of the pool, sort of a forebay. So water flows in, hits a forebay detention pool that might be 10 feet deep, slows down sediment deposits there in that detention basin. It reduces the sediment load to the wetland, which extends the service life. But these wetlands have a really long design life as it is, but that improves it by reducing it further. And then that detention basin can be serviced every 10 or 20 years as needed. It could be dredged out again.
So we talk about nitrate removal. One of the things that I think is very unique about the Iowa CREP program is from the start, there's been a monitoring component associated with this.
Right.
So can you describe kind of how many of these wetlands you might monitor in a year and what you do to quantify their performance from a nitrate perspective?
So we monitor, have monitored over the past decade or more, 10 to 15 wetlands a year. We're shooting for 20 wetlands a year now. And the monitoring is at the inflow. We have automated samplers that collect a sample every 6 hours. Those are composited into a single daily sample. Same thing at the outflow. So close interval monitoring of the inflows and the outflows, plus grab samples every week to supplement that. And then we have flow measurements, continuous flow measurements, either at the outflow structure or in the channel, right? So close interval data on flow, temperature, and close interval samples. From the automated samplers operate from as soon as we're able to get them deployed in the spring after the snow melt is gone, and we operate them until they begin to freeze up, typically now late November, early December.
So you mentioned when the auto samplers are out there, but if I understand correctly, your crew is out there even during those off months in collecting grab samples. And then what are all those samples analyzed for?
Yeah, so samples are collected year-round. The auto samplers only operate when the weather allows, from the spring through late fall. But we collect weekly grab samples at inflows and outflows year-round. The samples are returned to the lab. They're pre-preserved in the field as they're collected. They're returned to the lab. We do a full suite on nitrate and what amounts to total Kaldol nitrogen. So we do total nitrogen and nitrate, from which we can calculate the total reduced nitrogen or Kaldol nitrogen. And on phosphorus, we analyze total phosphorus and total reactive phosphorus. And we've done that on all sites for the past, more than the past decade.
So we've talked a lot about nitrate reduction in these wetlands, but you mentioned that in the monitoring, you're also analyzing for phosphorus. Do these systems remove phosphorus, and if so, how effective might they be?
So yeah, the wetlands do reduce phosphorus, but nowhere near the efficiency with which they remove nitrate. Really relates to what the phosphorus concentrations are entering the wetland. If the phosphorus concentrations entering the wetlands are high enough, the wetlands reduce the phosphorus concentrations. If the phosphorus concentrations entering the wetlands were really low, which is unusual, but if they were really low, the wetland can actually serve as a source for phosphorus, at least for a few years, right? Because these were former agricultural lands that were converted to wetland, right? So yes, they do reduce phosphorus, but we can't come close to meeting the nutrient reduction strategy goals for phosphorus using wetlands. I would suggest the same thing is true for every one of the edge of field denitrifying processes, saturated buffers, bioreactors, wetlands. None of those systems reduce phosphorus to any substantial amount.